Hey guys, Matthew here. This is the first video on mathematics for programming, and of course we're going to start at what I consider to be the very beginning, and we're going to talk about numbers. As you can see, I'm a big fan of MS Paint, and we're going to use some MS Paint to help us, just so I can sketch things out and there's no relationship to Grasshopper or Rhino or any particular software. So, the first number is 1. Not particularly surprising there that 1 is the first number. It's kind of in the name. It's kind of a tautology for the most part. But 1's quite cool. And then if I were to ask you the question, what is the next number? Instinctively, as a kind of kindergarten student, you would kind of deduce that 2 is the next number. And there's a lot going on there. Firstly, you're kind of saying that there is no number in between 1 and 2, which as you grow up, you kind of deduce is not necessarily true. And you've also kind of set up a system where we can go 3, 4, 5. And, there's no numbers between 1 and 2, there's no numbers between 2 and 3, there's no numbers between 3 and 4. So, this seems like an insanely minute point to be making, but the counting numbers are unique because of what they exclude. That they're the building blocks of kind of everything, right? So you go 1, 2, 3, 4, 5, blah, 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 blah. These are called the natural numbers. And there's some talk about if 0 is a natural number or not. But usually, I personally, do not think that 0 is a member of n, I think it's better off in a different set. But in computers, we always start counting at 0. So you might have noticed in some of the Grasshopper videos that the panels start counting at 0 and not necessarily 1. And when you think about, computers being obsessed, like on-off binary and all that kind of stuff, it starts counting at 0. So it makes a lot of sense to start counting in computers at the point 0. So let's, for the sake of this, call these types of numbers natural. Now the next thing we can do is we can say, well, clearly this goes on forever. I'm not going to prove that for you here. The other thing we could do is go the other way. -1, -2. And the reason why these are kind of considered a different set is because they're actually much newer than these ones. The idea of a negative number didn't exist for a long time. The Indian mathematicians discovered 0, and it was kind of brought back with Fibonacci, with the Arabic Indian numerals that we use today. And these are called the integers, right? Like a fairly fitting name, a name that you're quite used to. So this is, and that's represented by a Z, written in that kind of fancy way, which you'll have noticed was in the Grasshopper sliders video, but nevertheless, these are called integers. Any whole number can be negative, can be positive, and I'm sorry that MS Paint isn't the greatest thing for writing with a pen. Maybe I should get on top of that. All good. And either way, I can count forwards and backwards with these numbers, and that's really, really important because computers use numbers for a series of different things. And one of the most common things in parametrics is counting. First, do this to the first thing, do this to the second thing, do this to the third thing, do this to the fourth thing, do this to the fifth thing. Or how many points do you have? You can't have 2.3 control points on a piece of, on a NURB spline. You can't have 2.3 atoms. You either have it or you don't. There is no concept of division. But then when we think about space, and the space between numbers, the space between 1 and 2, and 3 and 4, That's much more useful at describing how far away am I from something, how tall is something, how big is a thing, what's the length of a curve, what is the exact coordinate of something that occurs, where do two curves intersect, and you'd expect it to happen between 1 and 2 and 3 and 4, then you would expect it to happen on 1 or 2 or 3 or 4. And there's a series of sets of numbers between them, and I'm not going to go through deriving it here because clearly I'm using MS Paint, and this is just a video to talk about the difference between counting and kind of measuring numbers. But the numbers that include, like pi and Euler's constant and a half and all these numbers that aren't integers, they're all in something called the real numbers, which is pretty cool. But there's certain numbers in there, like for example, if I look here, there's quite a famous number called the square root of 2, which requires a fair bit of precision. It can't be defined as an integer. As a fraction. So it requires a fair bit of computation. So these symbols come up, this one and this one, but it really should be this one, come up in Grasshopper's interface. But what these are actually talking about is they're talking about integers, counting numbers, and the reals are talking about the computer's approximation of a counting number called a floating point number. And a floating point number is actually a rather interesting construct. I will link to a video in the description that goes through floating point numbers in a lot of detail. They're quite amazing things. But this is a fundamental thing that you kind of need to be aware of, that we have counting numbers and we have numbers that are good at measuring. And sometimes they don't play well together. Sometimes it's important to know the difference between them. And sometimes they're interchangeable, which is a bit tricky, I know. But that's a really, really important thing to understand. So when you think about numbers, you're either thinking about the green numbers, the integers, -3, -2, -1, 5, 10, 20, 9,999, 81, 50, 40, 49, 48, all the different numbers. That don't have anything after a decimal point. Then you have floating point numbers, which include those. 3, 4, 5 are there, but it's more so like 3.0 and 4.0 and 5.0, but also pi, 3.1415, e, 2.7, the square root of 2, 1.41, I think, a half, 0.5. The numbers that have a decimal representation. And, as I just said, the integers can have a decimal representation, so they can also be expressed as a floating point number. But from the way the computer sees it, there is a difference, and it's important that we're just kind of aware that that difference exists here, because that will come up in the way that we kind of deal with things in this kind of course. Cool. All right. Well, thank you. I'll see you in the next video.